way, we are getting an overestimation. Getting kind of an overestimation. So it's like this is the error. So it's like unwanted things are added into my area. But I can reduce this error by increasing the number of points in the partition. And I can already see that. Before that, the error was, but now it is improved. If you make it even smaller, it's going to be even better by taking superiors. Okay. Now, so I am defining what you say upper Riemann sum for FT. So it would be what? So it's going to be similarly MI, which is basically what the supremum in the interval xi minus 1 and xi multiply with its height, with its width, and take the sum basically. So it's going to give me what? Fx. Okay. Now I can have lots of partitions of this basically. You're going to see that which of the partition is giving me minimum area. What is going to be, what do you say, our minimum error obviously? Okay. What would be the infimum of these UFPs? So F is fixed actually. So now you are taking infimum over the partition. You can have lots of partitions, but see that among these partitions, which is giving you the smallest upper Riemann sum. And that smallest upper Riemann sum, we are going to say, is going to give you kind of a rough estimation or a good approximation of this original function. Okay, is it making sense? That's what it's like. So after this intuition, I would like to write things more precisely. Okay. So we can have very interesting situations. Okay. We're going to see that. Can I get rid of this? Yes. That was a rough thing there. So as I said, that I'm defining F is fixed, LFP as sum I equal to 1 to n mi xi minus 1, and we have P as sum I equal to 1 to n capital Mi xi minus xi plus 1 actually. Okay. The difference now between both. Okay. Now I would like to prove some properties of these lower Riemann sums and upper Riemann sums. Okay. And then I'm going to define roughly the integral in the terms of lower Riemann sum and upper Riemann sum. That's what if we'll be heading at. I would like to define precisely what I mean by refinement of a partition. Okay. So if P1 and P2 are partitions of the interval a comma b such that P1 is contained in P2. Okay, so it's like P2 contains more points than P1. In other words, we have, so with respect to P1, you have less number of subintervals, and with respect to P2, you have more number of subintervals. Okay, so if P1 is contained in P2, we call P2 refinement of Okay. So that's one definition. Second definition that I'd like to write is that imagine I have two partitions, then we know that P1 and P2 both are contained in P1 union P2. Isn't it? Imagine if I just take the union of both partitions. But it's not necessary that P1 is contained in P2. If there are any two partitions that are contained in union, then this union is called the common refinement. Okay? It's called what? The common refinement of P1 and P2. Right? The definition, and then I'll try to define now. The lemma. Okay. So it's kind of give us basically, just think about it. So if I have a partition P1, then this P1 is going to have lower Riemann sum and upper Riemann sum. And P2 is also going to have a lower Riemann sum and upper Riemann sum. Question is, would there be a relationship between these lower Riemann sums of P1 and P2? There's going to be no relationship between them. That's what we'd like to see it. This is going to be something very useful for us. So imagine I have a function f, which is a function of a p into r, and it's obviously bounded. Okay. P is a partition. One is a partition. That's or that's n. Okay. Combination. Upper B. Okay. Over. Imagine I have a point S, which is other than A to B. It's between A to B, but it's not A and not B. And that P2 is basically what P1 union this S. So it's like what you are actually saying, that in the given partition you are adding a point somewhere in some interval. Okay. P1 union S such that obviously we want this S to be a new point. So obviously S cannot belong to P1. This belonging to P1, I'm not doing anything new. So if then the lower Riemann sum what do you think, what should be the relationship between
even contain
P1 content? These are numbers. So
less than sir.
what is your guess that?
Less than
So by intuition we can already see that it should be less than or equal. So in other words, your lower Riemann sum would improve actually. The error is going to reduce. And how about these two
Greater than.
should be greater than or equal. In other words, this contains more error while this contains less error.
Greater than in equal also.
आदि कंडीशन ट्रू होगा आदि कंडीशन ट्रू होगा
Equal in the sense, imagine,
and the subset p1 is
just think about it. Imagine S is really near to end point, but really near to one of the end points. That is not going to make it this. If it is in the middle of somewhere, it is going to make some difference. Area wise, you can have it, but cleverly chooses. Okay. So if I like to draw a picture, how does the picture look like? So I'm sticking with the same function. I said that imagine I have a bounded function defined from interval, and I have a partition. So this is x naught, this is x one. Okay. So I'm saying that S is not A and not B, it's a number between A to B. Okay. And it's not on each of these endpoints because S does not belong to B1. So where could be the S?
Between the
I don't know. So we're going to say that there must be a subinterval where this S would be. So let's call that subinterval as xi and xi prime. Where can be S can be N? Okay. That's what the picture looks like. Okay, what should be the relationship between P2 and P1? It is a refinement of P1.
finance.
Yes, you have P1, but you are adding something new to it. Here the proof. So suppose that S is in this interval. Sorry, should write I and I minus 1. Suppose F is between xi minus 1 and xi. Okay. Now we have read something very interesting actually. First, let's set out notation of infimum and supremum for this big interval. Okay? Imagine mi is same as previous one. So it's infimum of f of x, where x is anywhere between xi minus 1 and xi. Agree? Okay. And capital Mi is infimum, supremum, of f of x such that x is anywhere between xi minus 1 and xi. But now, since I have this point between them, so I have got now two subintervals. Now each of these two subintervals I'm going to have supremum and infimum. So let's give them name. So imagine I'm giving name W1 as infimum of f of x, where x is between xi and s. Xi minus 1 and s. And similarly, for capital W1 as supremum of the same. Okay. And for example, small w2 as infimum of f of x such that x is between s and xi, okay, and capital W2 supremum of all that. Alright? Now, I would like to show that this guy is smaller than or equal to this guy. So how can I show it? What should be the way to do it? Actually, just think about it. I guess. Okay. Take their difference and keep the difference. So imagine I have this LF P2 and I'm computing LF. Now tell me what's going to happen. Let's just think about it. Right? First, you may give a try and think that what should be this difference.
Sum of SIs. Sum of
The rectangles
which is size.
which are with this new partition P2 and the sum of rectangles, areas of rectangles, which are with the previous partition P2. So how about this area actually? So is this area a part of LFP2? This area. So it's like imagine I draw a rectangle and by taking the infill. Okay. By taking the infill. Is this rectangle, the area is included in LFP2?
Yes.
Would be because P2 is what?
Refinement.
P2 is not only refinement, but P2 is nothing. We just added 1 point actually. Okay, so it is going to be this. How about in this part?
Also.
So it's also going to be here actually. Just think about it. So I have area of rectangle in this, and area of rectangle also in this. So subtracted, so it's gonna be 0.
Zeros.
How about this interval?
This is
It's going to be again 0. How about, you forget about this, but how about this one actually? 0, 0, 0, 0. It's like everything is going to cancel out except this. Okay. So we are in this subinterval. Now, what is LFP2 in this subinterval? So I have 3 points actually now. Okay, let's think about it. I have 3 points. So it's like xi minus 1, s and xi. So what can I do? So I'm going to have 2 rectangles. This one and roughly this one. Okay. Now what will be the area of this rectangle, the first one? So this is going to be, first of all, what is the minimum here? We have named it W1. W1 multiplied by S minus xi minus 1 plus, what is the minimum on other subinterval actually? So it's going to be small w2, okay, small w2 and xi minus s, okay, minus What would be LFP1 on this whole interval? Is going, with respect to partition P1, this is nothing but basically just one rectangle. So what is the width of this rectangle? So xi minus 1. And what is the minimum in this rectangle? I. So you're going to have mi multiplied by xi minus xi. Agree? So you got this expression. So if we can somehow write this expression, and if we can somehow see that this is a non-negative number, we are done. And now my claim is that you can rewrite this expression by simplifying as this guy. You have to do yourself. W1 minus M1 times S minus Xi plus W2 minus Mi is Xi minus Xi. Okay? It's just simple, variation of this expression. Okay? Now, why this is an interesting thing? Just think about it.
W1 is greater than M1.
W1 is bigger than or equal to
M1.
So this is a non-negative number. How about this one?
This is always.
This is also non-negative because S is.
It's
It should be y minus 1, I guess. That should be I. Okay. So this is also non-negative because xi minus 1 is here and s is here, so take their difference non-negative. How about W2 minus Mi? So Mi is the infimum on this interval, which is this value, and W2 is what?
Infimum of.
Is infimum on the second interval, which is this value, which is already cancel the W this step. So we can see that this number is bigger than or equal to 0. Okay? It is bigger than or equal to 0. How about the second part? In other words, instead of taking now supremum infimums, take supremum set and take the differences of this interval. So what would be, you have P1 minus UFP2. Same is going to be the case actually. Everything is going to cancel out as we did previously, except the subinterval. Okay. So what would be the UFP1 in this subinterval? Capital MI, not M1, multiplied by the difference of the whole interval. Xi minus about capital W1 and S minus Xi minus 1 and minus plus minus capital W2 and Xi minus S. Okay. Okay? And my claim is this, that we can play around with this expression and it turns out to be similarly mi minus w1 multiplied by s minus xi minus 1 plus m1 or maybe mi minus w2 times xi minus si. Okay. Now mi is the supremum for whole big interval and w1 is supremum for subinterval. So what do you think, which should be the bigger? Huh? Mi should be bigger. Because we know that if a set is a subset of other, then its supremum should be less than or equal to basically what's the supremum. While in case of infimums, you have other way around. Okay. This is something that you have previously. So what we can say that this is non-negative and obviously this is also non-negative. These are obviously non-negative, so everything is non-negative. Okay. Right. Now, this previous result was about that imagine I have a partition and I added 1 point here. So I got a new partition. Imagine I add another point into it. So with the same argumentation, the conclusion is still going to be. So I can add as many as points into my previous partition. Okay? And then the new partition, which is a refinement of basically P1, is going to still have the same power. So in other words, I can propose this journal result. Okay. So that let's suppose again f is bounded. Okay. And P1, P2 partitions of A comma B such that P1 is contained in P2 in general. I don't know how many points. Okay. Not just P2 does not only contain 1 point but several points. Finitely. So it is going to be finite points. Then the conclusion is still true then. Okay. Then unless P1 is less than or equal to 2 and upper Riemann sum of f with respect to partition P1 must be bigger than or equal to upper Riemann sum of f with respect to the partition. Okay? What do you say are very fundamental? Okay? So, if you refine your partition, your lower sum is going to improve and your upper sum is going to shrink and reduce actually. And they will get closer to the original. Okay, so let's. If I compare, just think about it. It's a pretty much obvious question. For a partition P, if I say which is bigger, and left P are UFP. For some reason.
Yes, sir.
Why? Because
Less than.
this is overestimating area under F.
Yes, sir.
right? The P is underestimated. This should be explicitly prove it as well. Because Mi is less than or equal to capital Mi
Yes.
for all, because Mi is infimum, that is supremum. Then you multiply xi minus 1, xi and